In this second part of the video, we'll look at how we draw our bending moment diagram. So again, as was the case with the shear forward diagram, we'll start off by drawing a straight line to represent the line of zero bending moment. So I'll just draw this across here. And this line represents the beam, so either end is A and B, and the bending moment applying at point C on the diagram above this line will correspond to a position 2 meters along the length of this beam as well. So how do we draw a bending moment diagram? Well, what we're aiming to do here is to plot all the points of bending moment relative to a line of zero bending moment. So we label this 0 here and here to show us there's zero bending moment when we're marking a point on the line. First thing to do in any such diagram is to work out the bending moment for the points where we know forces are being applied. We have MA, that's equal to 0 because there are no forces or moments to the left of that point. We have MC, which is equal to a positive moment because of a clockwise turn at a distance of 2 meters away. So the force of 3.33 kilonewtons has been applied 2 meters to the left of C in an upwards direction. So this point is a positive turning force because it's a clockwise direction. So that's 6.66 kilonewton meters is our moment at point C. And at point B, the other end of the beam, we have 3.33 from the force applied at A, and that's now 6 meters from B, subtracted from the downward and therefore anti-clockwise moment at C of 5 kilonewtons multiplied by 4. Now, it won't work out as exactly 0 in your calculator, but with rounding, this is 0 kilonewton meters. And the reason for this is when we write 3.33, well, if you put in more and more threes, as would be the case here for 3 1/3, it would end up being exactly 20 when multiplied by 6, but we've done some rounding, so it's 0 here. Now we can plot these points on our diagram. We can plot the moment at A, which is 0, at this end of the beam where A occurs. I mark that in red. And for B, we can do the same. And for C, so a point about 1/3 of the way along the beam, representing the 2 meter mark, we plot this point here, representing 6.66 kilonewton meters. Now, these moments are plotted on the underside of the beam because that is where the tension is, because this is a beam that's effectively bending down the way, so are sagging, so there's tension applying in the opposite direction to counteract that. Now, we could just join these dots up, and actually that is going to be what happens with straight lines, but let's convince ourselves this is the case. So let's consider some other points along the beam. So I'll mark these in blue on the original diagram. So there's a point 1 meter away from A, this point here which is 3 meters away from A, this point here which is 4 meters away from A, and this point which is 5 meters away from A. So there's 4 additional points for us to calculate the bending moment. And I'm just going to call them M1 meter, M3 meters, M4 meters, and M5 meters. So this first point, the first of our blue points working from left to right, let's work out what the moment is there. So M equals M1 meter. That is just going to be 3.33 times 1. There's one force to consider, it's 1 meter away from this point, so it's 3.33 times 1, and that just gives us 3.33 kilonewton meters. If we consider the bending moment 3 meters away from A, of course it'll be 3.33 times 3, and we'll be subtracting the moment due to the force at C, but from this point, and this is the point, and we'll circle it in black here, although it's 3 meters from A, it's only 1 meter away from C, so this is going to be 5 times 1. And if we put that into our calculators and a little bit of rounding as well, we'll get 5 kilonewton meters. Now consider the point that's 5 meters away from A, and so will be 4 meters away from A, and so 2 meters away from C. We'll have 3.33, the force applied to A times 4, that's our distance from A, minus 5 times 2, because this point, and I'll now circle this one in red just to make it look different. That point there, I'll underline these in the colours. That point there's 2 meters from C. We can see that's the case. This point is 2 meters away from C, because it's halfway between C and B. And doing that calculation, 3.33 times 4 minus 5 times 2 is 3.33 kilonewton meters. I mean, again, you might get 3.32 in your calculator just based on the numbers we're using, but it's effectively the same here. And you shouldn't worry about that if you get a variation of 0.01 in a calculation. It means it's a rounding task. Now let's consider 5 meters and just use our full suite of colours. I'll circle this one in green just to show the point here. This point 5 meters away, well, as we come to expect, this will be 3.33 times 5. That's the moment due to this force applied at the left-hand side of the beam. And this point is now 3 meters away from point C, as we look to the left of this point. And so that'd be 3 times 5. So what we have here is 3.33 times 5 minus, so I've written 3 times 15 there. 3 times 5, because 5 is the downward force acting at point C. And we put this in, and we're left with 1.67 kilonewton meters. So let's take each of these points and put them onto our diagram. So we look at the 1 meter mark here. So this is the point here. We look down to our diagram at the 1 meter line. We want to move down 3.33. So that's half the distance that we moved down for 6.66. That's the 1 meter mark, 1 meter from the left-hand side. The point that's 2 meters from the left-hand side is C. We've already got that. So 3 meters away, well, we worked that out to be 5 kilonewton meters. So that point goes on here. The point that was 4 meters away, that was 3.33. So actually we level with our point at 1 meter, and that goes on here as well. And then lastly, we had the point that was 5 meters away. So 1 meter from the right-hand side, 5 meters from the left-hand side. So just about here. And that should be halfway from the previous point in terms of going towards the line. And we're left with a point here. Now, what we maybe thought instinctively the case is definitely the case now. We can see that there's a straight line, well, relatively straight line, I'm drawing on by hand here, that runs through these points. And if you look at the diagram in the course notes, you see it's actually a perfect triangle, just hard to draw freehand. And that's what we get in a bending moment diagram when we have point forces. What will happen is when we have point forces, so we have, if I'll highlight it in red up here on the shear force diagram at the top right, when we have these straight lines, because no force is being applied between these 2 points, that will correspond to a straight line on our bending moment diagram as well. So that's what's going to be happening here. We'll get straight lines in our bending moment diagram when we have these horizontal lines on a shear force diagram. And this is just one of the different kinds of diagram that we can get depending on how our shear forces are being applied. So that concludes this example.